Remember that this is the second video in a two-video example. In order to avoid the collision discussed in part 1, ship B changes its velocity to 22I plus 4J kilometers per hour at 1400 hours. We want to find the distance of A from B when they are at their closest and the time at which this happens, correct to the nearest minute. If we consider the first part of the question, we determined that the position vector of A was given by 2010 plus t times 10.5, and the position vector of B was given by minus 10 plus t times 25. At 1400, t is equal to 2 hours. Substituting this value in to our expressions for the position vector of A and the position vector of B gives us that RA is 40/20 and RB is 30/20. This is the position of A and the position of B at 1400 hours, which is when ship B changes its velocity in order to avoid the collision. As always, a sketch can help us understand this information. At 1400 hours, we have that B is at the point 30/20 and A is at the point 40/20. So here is B and here is A. Clearly they have the same y coordinate, so they're at the same height above the x-axis. The distance between them then is purely horizontal and must be equal to 10 units. B now changes its velocity. If we consider the relative velocity of B from A, this means that we're going to keep the position of A still, and we're going to see what B does relative to A being still. We've seen that this relative velocity is the velocity of B, 22.4, take away the velocity of A, which is 10.5, giving us 12 minus 1. If we now draw this new velocity onto our diagram, B will appear from A to be going in this direction. It goes 12 across for every one down. This is the velocity of B relative to A that we just calculated. The distance that we want, the point where they are closest, is just here. We'll also need to know this distance, since this will be needed to work out the time at which they are closest. Remember that B appears to be heading along this line. We want this angle. If we consider the relative velocity, it goes 12 across for every 1 unit downwards. We want this angle. So theta is going to be the inverse tangent of 1 over 12, which is 4.764 degrees, correct to 4 significant figures. Using 4 significant figures, because I want to give final answers to 3 significant figures, and since this will be used in intermediate calculations, we should store extra significant figures. We can now readily calculate d. Looking at our triangle in the diagram below, we can see that d will be 10 times the sine of 4.764 degrees, and this is 0.831 kilometers, correct to 3 significant figures. X, which we also need to know, will be 10 times the cosine of 4.764 degrees, and this gives 9.965 kilometers, correct again to 4 significant figures. Since this is an intermediate calculation, we need the extra significant figure. To work out the time for this closest approach, we need to work out how long, at the relative velocity, bva, b takes to cover the distance x. We need the magnitude of the relative velocity. This is going to be 12 squared plus 1 squared, just using Pythagoras' theorem, and calculating this gives us 12.04 kilometers per hour. The time taken then will be the distance, which was x, divided by the speed, 12.04, and this gives 0.827 and so on hours. If we multiply this by 60, we'll get the number of minutes, and this calculates to 50 minutes to the nearest minute. The time at which they are closest then is 1450, 50 minutes after ship B changed its velocity.